Alexander, and thank you for having this call with me today. I asked you to repeat a presentation that you guys have done before. You presented internally at our RHI Magnesita to your colleagues the project we're working on. And I listened in and I thought it was so interesting that I asked you to repeat it so we can share it with our community.
Yeah.
I do not want to lose many words now. We just start and just jump in.
Thank you.
Please tell our audience what you told your colleagues last time.
Thank you, Carmen, for the introduction. Yeah. So, hello, everybody. I hope you all have a very good morning today. So I would like to introduce myself. I'm Dr. Saranya Azhaarudeen, and I'm working as an innovation management professional at RHI Magnesita, and I'm also the project coordinator of ReSoURCE. Yeah. So what is ReSoURCE? ReSoURCE is the project that we got funding recently from the European Union, which stands for refractory sorting using revolutionizing classification equipment. Yeah. And it is the first time that we got such a funding where our company is leading. So I'm really proud to present to you all today about ReSoURCE. Yeah. And me today will present about the administrative stuff and what we are doing with regard to management. And my colleague, Alexander, will really give you a very detailed explanation of the technical scope of the project. Yeah. So hopefully you enjoy this presentation. Yeah. Alexander, could you please change to the next slide? Thank you. So what we do in innovation management from my area, yeah. So my area is like taking care of funding activities, yeah. Mainly, for example, we RHI Magnesita is a global company, so we are headquartered in Vienna, Austria, and we do have a lot of global locations like in Brazil, India, and China. And what we try to do is that we are trying to create an overview about global funding activities, like what is already happening in different parts of the world and what is possible and what could we achieve in the future, yeah, in different areas, like what our company is focusing on. And what we try to be in innovation management is to be a point of contact, like a central point of contact, where when there is any request with regard to international funding request, it will come to us and then we will check, yeah. And after that, when we have one point of contact or when we have any questions, and then we try to screen the funding opportunity suitable for that particular project, yeah. And then if we think there is a particular funding opportunity suitable for this particular project, and then we try to spread this information to our colleagues so the colleagues can think of it and they think if this funding opportunity is suitable or if they have suitable partners to go on to the funding opportunity, yeah. And what we try to do next is this management, yeah. So when we see, yes, one funding opportunity is available and yes, we are trying to go for it, then we want to manage the project, yeah. So once we say, yes, we are going and we got the funding, we want to manage the project in various international funding portals. For example, in Europe, it's Horizon Europe, it's European Union portal, and in USA, for example, is the Department of Energy, yeah. So we try to manage these portals for our colleagues. And then we try to administer, and we do a lot of administrative support for proposal submissions. And whenever there is any type of questions, the colleagues can come to us and then they can ask these questions, yeah. And what about forum membership? And RHI Magnesita is very active in various forums like Ceramiuni in Belgium. And we do have a lot of forums for steel and iron industry where we are very active. And we try to also get a funding opportunity and we try to do some lobbying activities in European Union for that. Yeah. And what we do also, we do active networking just by participating in such activities like Ceramiuni or any networking activities for Horizon Europe. We try to get more information for internal and external networking. Yeah, so this is what we do in a nutshell at innovation management. So can you please move to the next slide, Alexander? Thank you. So what is the key facts from ReSoURCE? Yeah. So ReSoURCE, as it stands, as I said, it's a funding from EU Horizon program, where it was funded under Twin Transition Program. The total project budget was 8.5 million euros. And the funding that we got from European Union was 6 million euros, where 1 million euro came from UK innovation and research sector. Yeah, since we had a UK partner, they got direct funding from this UK RI. And then what is the funding rate? We got a funding rate of 70% for as an industrial partner, and then 100% for research partners who are as a university or a research organization. And as I said before, first time RHI Magnesita is leading such a big project, and it's the first kind of experience for us also to lead such a big European project. And the duration, we started in June 2022, and we will end the project in November 2025, because it's planned for a total month of 42 months. Yeah. And consortium, we have 9 members, where 4 are academia and 5 are industry from various countries like Austria, Germany, Norway, Ireland, and also UK. And FTEs, we have full-time equivalents like 18 in total, and 30 people from 10 different nations. Yeah. And could you please move to the next slide, Alexander, please? Thank you. So RHI, what we do in RHI as a project coordinator, we perform the following functions. Yeah, we try to manage the technical and administrative affairs, and then we do technical role in project, like the technical project team, because it's Alexander who's leading the technical project team. He will take care of the technical stuffs of the project, that we do achieve what we promised to European Union, and coordination of project meetings, that I will take care that whoever needs any project meetings, we will try to have project meetings for project management as well as for different work packages in the project. And reporting to the European Commission, which is the very important duty that we are doing. Until now, we have delivered already 2 deliverables and 1 milestone successfully within the time deadline. Yeah. So please, could you move to the next slide, please, Alexander? Thank you. So we have different partners. As I said, we have LSA from Germany. We have Innolas from Germany. We have NEO from Norway. We have Fraunhofer from Germany, Montanuniversitaet from Leoben, SINTEF from Norway, CPI from UK, and Crowdhelix from Ireland. Yeah. So we have different partners to do different stuffs. Yeah. So LSA is taking care of the installation, Innolas, and Fraunhofer is doing the simulation stuff for artificial intelligence, and NEO is taking care of the multi-camera stuffs, and SINTEF is taking care of the sorting techniques, and Montanuniversitaet is also helping us for sorting techniques, and CPI is taking care of the life cycle assessment, and Crowdhelix is taking care of the Helix platform. Yeah, so we have different partners contributing for different things in the project, and we're really happy that we had a fantastic consortium. Yeah, so could you please move to the next slide? Thank you. So what we do in the resource as a whole, as a management, yeah. So we do try to manage as a whole everything in the project, because it is important to have the administrative affairs, because RHM will manage, coordinate, and monitor the whole administrative affairs in the project, such as the compliance with the EU regulations, because whenever we do have a grant agreement with the European Union, we do have to follow some regulations to the project, and we try to follow that we are within these regulations. And we will also manage the funding, and we also manage the budget in the project and financial reporting. If we have budgeted more or if we have budgeted less, we have to manage the budget as well in the project. And reporting, we want to communicate to the European Union about the reporting, like deliverables, milestones in the particular deadline, and RHM is responsible for all the partners on behalf of the consortium. And workflow, we will try to see if the technical progress is meeting the project's objective, and it is in the particular way that we plan. And if there is any change, we are the ones who should communicate everything to the European Commission through EU project officer. Yeah, that's the main part of communication. And time-wise, we will manage the project, we will schedule, and we will also do the time reporting, that whoever is working in the project, we do have to have a time reporting sheet, and that we are working for the project as we planned. Yeah, so this is what we try to manage this as a whole in resource. And that's all from me. I think I had produced like a very small introduction about the administrative stuff. And now it's time for Alexander, who will give a very detailed overview on technical things. So thank you so much. So Alexander, go ahead.
Okay, yeah. Thank you, Saranya. I think that was already quite an interesting overview of the administrative efforts we have to take here. Of course, you see there's really a lot of effort you have to take also on this management side. But we really think, considering the technical scope and the technical developments we can do in this frame, it's really worth also doing such a big project here. Before I will going on, I really would like to acknowledge the entire team we have here in ReSoURCE. So it's really, so far it's working great. So we are really good in communication. We are having a lot of meetings together. And I think that's really the base for success of this project. Yeah. Before I start, I just would like to read out the title again. Yeah, so it's saying refractory sorting using revolutionizing classification equipment. So that should make it clear that it's really about a sorting unit for refractories. And in the next few minutes, I would like to describe a little bit why we think this is so central for refractory recycling, and also explain a little bit on one example where we see the big benefits for having such a big multidisciplinary consortium as we have here in ReSoURCE. Okay, so about project scope and targets, right? I think overall it's well known that in general recycling brings a lot of benefits, not depending so much on the raw material. Yeah. So on the one hand, of course, it's always about CO2 savings. It's also about energy saving, and it's also about preserving natural resources. I think that's always common if we talk about recycling. And just because of these 3 points, I think it's really worth doing such a big project. Yeah, of course, there are also other agendas we have in the European Union, and also if we think of national climate action plans, for instance. And part of that is also always that we have better educated people. So that means upskilling, that we also go towards a digital transformation. So we somehow also have to find new ways and more efficient ways to do our processes. And of course, also to strengthen our resilience in the European Union to reduce our dependence of other regions. Yeah, so that's very well in alignment also for refractories with these agendas there. And core of this project is the falling technology gap. So I would like to explain a little bit from the process overview of a refractory product. Yeah. So when we do a lining, so that means we install kind of bricks or other products in a customer aggregate. We install, let's say, 100% of these bricks. Yeah. Now, our material is also a consumable. That means that during the customer process, for instance, in the steel industry, it could be a steel ladle, about 50% of this lining is consumed. So we will never get back 100% because this material is now simply also in the customer product. When this process is finished, customers will do a breakout there, and we will receive back a material we could reuse in our products again. Now, because of this breakout procedure, we are facing some challenges, I would say. So a big challenge is actually that some of this material will not be or will not come back in big parts. It will rather be small parts. Yeah, it's not very economic to take it for an operator anymore. So the only thing left in the current state of the art is about 20% of this material, where we have a big enough grain size that it's still feasible to do manual sorting. In some cases here, there are products out there which you cannot really distinguish as an operator, so this will also be unsortable. And that means at the end of the day, from an installed 100%, we can only reuse 15% really in refractory products. So you really see that most of this material, which is still there, even after the breakout, cannot be used because either it's not sortable or it's just too small to be sortable here. And that, unfortunately, goes along with a lot of landfilling currently, and on the other hand, with some downcycling in non-refractory applications. That's exactly the technology gap we would like to bridge by using this project ReSoURCE. So just an impression from the field. I mean, is it really the case? Do we really have this problem, or is that just from literature? I think we have a lot of experience on that, and we have seen really a lot of piles out there, also in Central Europe, all over Europe actually. So we really see that the problem is there, and this is also something the customers would like to find a use for. So I would say we can definitely confirm it's worth working on that. So, well, what's actually now the big challenge with automated sorting? Automated sensor-based sorting is out there for many different industries already, but still in refractory we are lacking a little bit to find a solution which is suitable to address the problems we have. So before, I would like to show you just the benchmark of the automated sorting for nowadays, which is manual sorting. So the manual sorting sounds easier than it is, I would say. Yeah. So we have several process steps. So the material comes in, it needs to be singularized, which like an operator can just take a brick. Then in many cases, the operator has to break the brick because just the outside or the surface is not representing of what's inside this. Then very often we have some attachments from the process of the customer, like attached slag or attached clinker from the cement industry that has to be removed. It's also done by the operator, and then he has to classify it. Yeah, and classification is not simply done by color. It's actually a mix of different properties a human can spot there. So it's in color. It's also the patterns of the raw materials he can see at this fresh crushing surface, for instance. But it's also just about shape and geometry of this brick. Yeah? Sometimes also the sharpness of the edges can tell you something. Or also, if he just lifts it, he will already get a certain idea of the density because he knows how big it is and he has a certain feeling of the weight. And so it's really quite impressive if you have a manual employee there doing this job and seeing how accurate they can actually work. At the end, yeah, it's also ejection, so he can put it to a box, whatever he wants to. If you would like to go for automated sorting solution now, of course, we somehow have to reproduce all of these tasks, which you can break down in another few tasks. So altogether, the automated sorting machine has to cover 25 different single tasks, I would say. Yeah. So that's already quite challenging. I think the biggest lever we have in general for this project is really to getting access to smaller grain sizes of this material. Yeah? So doing all these steps, 3 pieces per minute, that's already quite tough to do, I would say. But of course, if you combine that now with the average particle size you have, you see that there's a border of this around 6 kilogram of the average particle this operator should grab in order that he can achieve average throughput of 1.2 tons per hour. Yeah, that's really a lot already, but that's also what we need to be really efficient and also economic. Yeah, what we compare to our primary raw materials. But I would say that's not the full story at all. It's not about replacing the manual sorting people here. It's just that we would get a lot of other benefits if we do the automated sorting here. So the first one I mentioned before, that's the limitation in grain size. Yeah, so that will never be possible by a manual operator. Second important thing is that we are also lacking chemical information if we do just this manual sorting. Yeah. And this goes along with minimal process data because that means that actually he is doing the decision for each piece, but it's actually not so easy to retrieve the data and to understand afterwards why this decision has been made. So we are not like filling any databases by these decisions. And then, of course, we have to admit here that it's very dependent on the experience of the operator. It's not so easy to find here operators who do this job for 10, 20, 30 years, right? Because it's also a tough job and it's the environment is quite challenging. And last but not least, of course, also if you have an experienced operator, it's not so easy for him to really pass this experience to other people, especially if you think of very different region. Yeah, so we have simply no central development now, which of course would be possible when we are using these automated sorting facilities. For ReSoURCE, so now how would we like to tackle these automated sorting systems? Yeah, so I was talking about different grain sizes now. We will basically split that into 2 demonstrators. There will be one demonstrator which is operating with particle sizes from 5 to 120. Here we will do development of 2 sensors, which is laser-induced breakdown spectroscopy and hyperspectral imaging, and we'll try to recover as much material in this particle size range. Yeah, and here the measurement setup is that we will measure each individual particle being on the conveyor belt. If you are under the limit of 5 millimeters, that's simply not possible. So even for highly automated systems, these particles get too small. And so we are also looking to have a demonstrator B, but it will be more kind of batch analysis. And this will also be a machine which we design from scratch, based on the findings we have from our characterization. Yeah. So now also one word on the project again. So we are not only addressing the sensor analysis and the automated sorting machine, we actually really try to tackle the entire process value chain of automated sorting. So we will start with a really deep analysis of the material feedstocks we are going to process. That's quite challenging because you consider this as kind of micro deposits. And now every target industry for refractories has different products, but also have different challenges for how to treat this material. And that we really need to find out in this first work package, which is mainly about feedstock selection, characterization, but also sample distribution. So if you get this material, we know that we, of course, also have some boundary conditions in terms of size for the automated sorting machine. I mentioned this 120 millimeter limit before. So that means that in a way, we also have to guarantee that there's no material bigger than that. And for that, we are looking for optimized crushing and cleaning pre-treatment of the material before it enters this automated equipment. Then also, sometimes underestimated, I would say, there's the feed to the sorting equipment. Yeah, that's not so easy that you can really guarantee a continuous feed there. We are talking about machines with throughputs of up to 5 or 7 tons per hour. So you also have to somehow supply the material continuously here. And then still one of the core packages is really the sensor combination we are planning here. So we try to break ground by combining different sensors in order to get the most robust, most reliable classification of refractory products within this project. And here, that's exactly the topic I would like to present you a little bit more in detail later on. We are not only working on the energy source you need for that or on the sensor side itself, we are really try to integrate everything within this project by having different partners for the individual process steps here. Now, okay, we have data. So the sensors are actually just generating data. Now we also have to find a clever way of how to analyze them. I think artificial intelligence is quite a well-known topic nowadays. And if we think of capabilities like ChatGPT and so on, it gets quite obvious that there's really a lot of benefit in such AI-based data analysis, especially if it comes to big data amounts as we will have here from the different sensors. So here we will have a big work package as well just on the data analysis. After that, of course, if you classify it, you still have to find a way how to put all the particles in the designated bin for it. And that will be the ejection optimization here, which will be either done by pick and place robots or by air ejection. And then, of course, we will have sorted material, which will be quite different from what we know nowadays from manual sorted materials, because we will have other information, we will have other classification criteria. So we will also need to work on new product concepts for refractories, but also for waste streams we cannot utilize within the refractory product. And on top, again, of all of that, we are carrying out the life cycle assessment and the techno-economical analysis, which is quite important. So also that we really know what's really the sustainability benefit of this, and that we are also aware that we have certain emissions also from recycling processing here. Yeah, and now I would like to give you just a brief example here on sensor setup and material classification work package. So I was mentioning before that we are using this laser-induced breakdown spectroscopy, yeah, with the acronym LIPS. Just very short on the principle of this sensor. So we have a laser emitting very short laser pulses, and by an optical system, you can focus then on a material because they're very short. They still carry a lot of energy. Yeah? So that means they are creating a plasma on top of this material with a temperature of 5,000 to 10,000 Kelvin. And the color of this plasma will be led by a glass fiber to a spectrometer. Now, maybe you know this experiment from physics where you have a prisma and it will split the white light in its different wavelengths. That's exactly the same what the spectrometer is doing here. So depending on the color now of this plasma, you will be able to record different wavelengths, and these wavelengths you are getting there, they are specific for the different elements you have in your material. So this is really kind of how to get a chemical analysis. And now you read here, well, it's a measurement frequency of 100 Hertz, 100 measurements per second. That sounds a lot, but still, if we consider the structure of a refractory, that's maybe not so straightforward for us that it's really feasible. So I would just like to explain a little bit, these systems especially emerged for aluminium metal scrap sorting because it has certain advantages in terms of measuring light elements such as aluminium, silicon, magnesium, which are very relevant for different alloys you have in the aluminium industry. Yeah. Now, by coincidence, that are also exactly the elements we deal with in refractories, but the difference is simply that this aluminium scrap, it's very homogeneous. So within a few micrometers, you will actually have really a representative volume of its composition, while this is by far not the case in a refractory. So the cylinder I'm showing here that has a diameter of 50 millimeters, and you see that there are, for instance, this grain here would be a MgO grain. So if the laser is shooting on this point, it will only measure MgO, but it would not cover anything in the matrix, yeah. But also these are quite important. So what we have to do is not to only have one pulse on the material, but multiple per particle. And then you see that, of course, also considering the measurement frequency limit we have, that's really reducing a little bit the throughput of our machine. Yeah, so you see, it's very well working for aluminium, but if we would use a commercial solution now for refractories, we would really have some limits. And now that's where ReSoURCE comes in. So actually we have Innolas with us on board. So they will have the chance to really modify already the laser in a way that it's a benefit for us. So we will have higher laser powers. We will have probably even a faster laser here. And that's quite important because we always would like to increase the volume here. Okay, now we are changing the laser source. Seems straightforward, but that also has an impact now on the spectrometer, yeah? Because like the plasma would probably have a higher intensity here, so you also have to change the spectrometer. So now here we are in cooperation in this project with LSA, who are experts in designing such spectrometers. And they will create, based on the new laser source we have, a new spectrometer. And then again, having now a new spectrometer, having a new laser source will certainly impact also on the data analysis. Yeah, so we need another strong partner, which is Fraunhofer in this case, who will do this AI-supported data analysis here. And you see, so if you would do that really only on your own, you would have to get in touch with 3 different partners, and it would be a lot of effort if you do that outside of such a project we can do here. And it would also be honestly very costly to do that. And then a second thing I would like to mention here now, so that was just the first part on the lips. On top, we are not only would like to add lips, but we also would like to add the second sensor, which is hyperspectral imaging. Yeah. In principle, the biggest advantage of this is that you can really measure the entire surface of your sample. So it's not a spot measurement as the lips before, but you can really detect nicely the entire surface. It's a bit different to a regular RGB camera. Yeah, so actually it's very different because a regular camera is only detecting 3 different wavelengths, while this one, we collect a few hundreds of these. Yeah, so instead of 3 values for a red, green, and blue, you would get here a lot of values for the according wavelength. Yeah, and this reflectance curve you see here, the spectral curve, will give you some information about the chemistry and also of the phase composition of this material. I'm not going into too much detail into that. I just would like to show you a very nice example on that. So this is a cross-section of a brick we get back from cement rotary kilns. And even though you can see that visually that there are some differences, this camera really nicely allows us to classify different zones and also to link the zones really to certain elements. And now what we would like to use this camera for is to get a pre-information of the sample to make afterwards a clever selection for the lip spot where to measure the material, which will overall then allow us to measure more particles. Yeah, and now again, that's just the beginning of the story. It sounds maybe also easier than it is, because if you combine now 2 different sensors, actually we are adding even one more. It's a 3D image topography we do. They also have to be somehow aligned. Yeah, so that means that data which is coming in from the HSI has to be processed before the particle is reaching the lips, because otherwise it would be too late. Yeah, so you have also to be fast here. And that's a quite tricky task, which is also carried out here by the Fraunhofer Institute, who have a lot of experience on this topic. Yeah, so just as an example here, sometimes materials are very inhomogeneous, so it would be really a benefit to know if we will shoot like on a contaminated spot or maybe on a fresh sample surface. So we are very convinced that this will increase drastically the efficiency and also the correctness of the measurements we are doing here. And then on top of that, what I've mentioned before, just to mention here as well, the chemical, so we will get a lot of chemical and mineralogic information, which we will not get by manual sorting. So also in terms of specification, we will have much more data available after this sorting task, which will be a big benefit for us in the usage of this material later on. Yeah, before I come to the end, I would just also like to address an important topic we have here in the ReSoURCE project. So we really have some capacity here to spend a little bit on communication on the ReSoURCE project. I think that's sometimes a topic which does not get a lot of attention, but I think it's really essential to have a project success here. Yeah, and principle, what we of course have to do in that way is to have really stakeholder engagement. Yeah, so I think before we even implement the technology, the stakeholders have to be aware of it. They should be engaged so that we understand if there are any obstacles upcoming for that. And stakeholders does not only include internal people making decisions on investments, it's also the general public, it's technically interested communities, but it's also academic and experts. So getting feedback is always very important here. Now, one way of really getting in touch with them is blogging and social media. Yeah, so here we can share some personal insights. We can somehow encourage them also to be interactive. And we have already now seen in the first 8-9 months of our project that this is really working. So we have already a nice network. We are getting addressed by the right people. So that's definitely helping the project also in the midterm to be successful. And may also not to forget, of course, academic activities. This is definitely a growing field. So we have to get in touch with experts now to increase the awareness also on the academic side so that we can also promote and support new science fields at university. I think that's quite important because after some years we will need a lot of people who have this expertise so that we are able to effectively and efficiently work or continue the work on that. Yeah. So just mentioning here, overall, I think it's really drastically increasing the success chance of this project, and it will also increase the exploitation in future. Yeah, so we will really also have monetary benefits for the entire European economy from that. Yeah, and so that's some final remarks I would like to give here. So for me, the take-home message would always be that public funding is not only about raising money. It's not just to pay your lab analysis. It's much more than that, right? So you really will have to have the chance to have a tailor-made technology development. Yeah, what I explained to you before. But you're also creating a very, very strong cross-industrial and academic network. I think that's quite important because if you are together in a this resource project for such a long time, it's really a good relation you have and will also make it easier to address the right people in the right moment. Of course, not to forget, there's also joint IP generation. So we are also going to license that. That's a big benefit here as well. And we always have the support also from academia to also get really there very good expertise and inputs if the things we're doing, if they are really in alignment with the current state of the art. Last but not least, of course, communication to the broad public, especially refractory is a kind of hidden industry for the general public. So also if you're interested in following this project, feel free. We would be actually very happy that if you would follow either on our webpage, our LinkedIn or our Twitter here. And with that, I'm at the end of my study, and yeah, just like to thank you for listening and again acknowledge the great resource team you see here on the right hand side. Thank you very much.
Thank you so much, Alexander and Saranya. Yes, I can only encourage everybody to follow our blog and our LinkedIn postings and all of that, because you really get an insight in this project. You can see the progress that's made, and you can get a lot of background information that maybe is not common knowledge. So thank you both again for sharing that.
Thank you, Carmen, for organizing this talk. Thank you. And thank you, Alexander, for such a nice
a lot,
explanation.
Goodbye.
Bye.
Bye.